6.8 Directionality of Processes. An entropy balance is expressed here. An isolated system is an adiabatic closed system, so there is no mass and energy transfer between the system and the surrounding. As there is no heat transfer, delta Q over T drops out. The entropy of an isolated system always increases for actual processes, and it is zero for reversible processes. So the entropy productions or the entropy change for an isolated system is always greater than zero or equal to zero. The entropy of an isolated system can never be negative. The only way that the entropy in the closed system decreases is by losing heat. But there is no heat transfer to the isolated system. On the other hand, the entropy increase of an isolated system is caused by the irreversibilities, not by the heat transfer. The entropy of an isolated system is sum of the entropy of the system and entropy of the surrounding. Consider a system within the isolated system. This is isolated system. And we have another system inside the isolated system. Mass going in and out of the system. Also, there's a heat transfer to the system. Also, the work is done by the system. So this is the system and this is surrounding. So the surroundings of the system is also within the isolated system. So there is some process whereby the system receives heat from the surroundings and work is produced by the system. So mass goes in and out of the systems. But notice that both the system and the surroundings are inside the isolated system. They may be considered as two subsystems of an isolated system. The subsystem means it is a part of the isolated system. We know that the energy is conserved during the process. We can apply the first law of thermodynamics to the isolated system. But the entropy is not conserved if it is an irreversible process. So take the entropy balance for the system and the surrounding. So this is the entropy balance for the system. And this is the entropy balance for the surroundings. So add the two equations. This cancels out. So the left-hand side is the sum of entropy change in the system and the surroundings. So that is the total entropy change in the isolated system. And the heat transfer terms in the right-hand side cancel out. Both the entropy production by the system and surroundings are positive. So the entropies add up. So the total entropy increase is not conserved. So on the right-hand side, total entropy can be written as sigma isolated system. If the process is reversible, the entropy production of the isolated system will become zero. And this concept is known as the increase of entropy principle. Let's work on the example to better understand the increase of entropy principle. A 0.8 pound metal bar initially at 1900 degree Rankine is removed from an oven and quenched by immersing it in a closed tank containing 20 pounds of water initially at 530 degree Rankine. Each substance can be modeled as incompressible. An appropriate constant specific heat values for the water is Cw. Specific heat for water is 1.0 BTU per pound degree Rankine. And an appropriate value for the metal is Cm. Specific heat for metal is 0.1 BTU per pound degree Rankine. Heat transfer from the tank contents can be neglected. Determine the final equilibrium temperature of the metal bar and the water in degree Rankine and the amount of entropy produced in BTU per degree Rankine. So we take the water and metal bar in the tank as the system. This is a closed system. There is no energy transfer by heat or work. We consider the system as an isolated system, since it's an adiabatic and no energy transfer. First, we are going to determine the final equilibrium temperature. So we perform an energy balance on the system, including the metal bar and water. So this is basically the first law of thermodynamics. The tank is stationary, neglect kinetic energy change and potential energy change. There is no heat transfer, no work associated with the process. So the only thing left is the internal energy change of the system equals 0. The system includes metal bar and water. So we can write it as internal energy change of water and internal energy change of metal bar. Both the metal bar and water are incompressible substances. So we are going to use the incompressible substance model to determine the internal energy change. So the internal energy change for incompressible substances constant volume specific heat equals constant pressure specific heat, and it is denoted by C without subscript. And we also assume it has a constant specific heat. Typically, specific heat is a function of temperature, but we are going to assume specific heat is constant. So for constant specific heat, it can be further simplified. Internal energy change is C times temperature difference. So this equation becomes And the only unknown here is TF, final equilibrium temperature. And so we solve it for TF. So the final equilibrium temperature is calculated. We also need to determine the amount of entropy produced during the process. So the entropy generated during the process can be determined by applying the entropy balance on the system. So we write the entropy balance equations. Since it's an isolated system, delta Q over T drop out. So the entropy production is equal to the entropy change of the system. For incompressible substances, entropy change can be written integral T1 to T2 specific heat C over absolute temperature dt. And we assume specific heat is constant. So it can be written C times natural log T2 over T1 for constant specific heat. So the entropy production is delta S of the system. And the system includes metal bar and water. And the entropy change is expressed as specific heat times natural log T2 over T1. So we plug in values. So this is the entropy change of matter, and this is the entropy change of water. So initially the metal was hotter than the water, so metal lost heat to the surrounding, and water gained heat from the metal. That's why entropy for water increases, entropy for metal decreases. But the entropy generation of the system is positive. That tells us that the entropy in the isolated system increases after the process. This is caused by the heat transfer between the metal bar and the water inside the system.